Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody from the future. So, last week we had fun of probabilities, and this week we are also going to have fun with probabilities. We are a bit ahead of time. That's actually great news because it means we can take the time to go through questions. I even have a few clicker questions for you today. So I will wrap up on this part of the lecture, and then I will discuss language models, not the large ones, the small ones that have existed for a very long time. Okay, so let me start with a few clicker questions for you, and then I'll go through the rest of the material here. Okay, so what do I have? You can see I have a few prepared here. Let me do this one. Which of the following does not always apply in probability theory? So the first proposed answer is that the sum of the probabilities of all elementary events must be 1, or each elementary event must have a probability of either 0 or 1, or a probability must always be positive, or the probabilities of elementary events must all be equal. Which of the following does not always apply? Multiple answers possible. I mean standard probability theory, the one at the bachelor's level. Okay, the number of answers is stabilizing. Let's see what we have. We have consensus on these two, and this is correct. So these are the ones that do not always hold. Let's start with the ones that always hold. So first, the sum of the probabilities of all elementary events must be 1. This is just a renormalization, right? So you have measure theory in mathematics where you can assign a measure to some sets, discrete or infinite, even uncountably infinite. And probabilities are a special case of measure, but it's the special case where we renormalize to 1 for the entire omega space, right? So it's really a renormalization. Okay, so yes, it is always true that the sum of probabilities for the elementary events must be 1. The elementary events, remember that these are the members of omega. An elementary event belongs to omega. It's a member of omega. This is not to be confused with the events, not elementary, the events that are subsets of omega, right? And a subset of omega contains elementary events, and the probability of an event is it's the measure of that event. It's the sum of the probabilities of the elementary events that are inside that event. Okay, so this is always true. A probability must always be positive. Yes, in standard probability theory, this is true. I realize I might wanted to say even non-negative because in English positive might imply it's not 0. It can absolutely be 0. So a probability cannot be negative, cannot be less than 0. Now I'm going to open a parenthesis because this is kind of cool. It turns out that you can extend probability theory with negative probabilities. That actually works. And there's a beautiful paper that I recommend reading if you're interested by Richard Feynman, who discusses this in quantum physics. And the idea is a bit similar to, it's something very common in mathematics. You all know what a complex number is, right? I. So if you look at the history of how that was invented, the very early days of that is that people realized that there are polynomial equations that were difficult to solve, degree 3 and more, and even 2. And then they realized that if you actually invent or make up some number that doesn't actually exist, you just posit it this way, that you call I, and that you assume that I squared is -1, and at that point is just something made up, then it means that you can play with numbers, and every time you see an I squared, you just replace it with -1, and you can just pretend that you're manipulating numbers. And the big surprise is that you make up that number and suddenly you manage to solve equations because you can write things that you couldn't write before. And so we made up I to be -1. So now we actually know it's not made up because you can actually define I. If you take the set of polynomials and you probably, if you visited discrete mathematics and so on, you know the quotient sets with an equivalence relation. So it's basically done by taking the set of polynomials, and then you look at the Euclidean quotients by x squared plus 1. Then you take the equivalence relation with the modulo. So two polynomials are in the same equivalence relation if they differ by a multiple of x squared plus 1. And then when you take the quotients, turns out that you just invented the set of complex numbers. So now we even know how to build it. And so negative probabilities are a little bit the same. The idea is that in the real world, of course, we never observe negative probabilities. They're always non-positive. But while you compute things, it's kind of okay to accept that there could be the negative probabilities in the middle of your computations, as long as at the end, it's again non-negative. And so this was the idea of Rich Feynman. But again, parenthesis closed, I just want to say that this is in the standard case that we don't accept non-negative probabilities, but you could actually build a theory that contains them in the realm of quantum physics. Okay. Then what do we have? Each elementary event must have a probability of either 0 or 1. No, it can be 1/2, 1/3, can be anywhere in between, right? In fact, if they all had to be either 0 or 1, that would be a certain configuration, right? Where you have just one elementary event that is 1 and all the others are 0. That would be the only possibility. And this is when you get the minimal entropy with everything is basically known. And so that is obviously not always the case, because otherwise that would be extremely restrictive. Then probabilities of elementary events must all be equal. No, that's not true in general. What do we call the probability distribution? If that's the case, we call it? Yes? We call it? I didn't understand. Laplace. It might be connected. I just had in mind the uniform, that it's uniform, but there might be. I will look at it offline if there's also a connection. But I had the uniform ones in mind. Okay. All right. So far so good. Who is with me? Right. So if you're in your 3rd year of bachelor's, you've seen it last year, and if you are currently seeing it at the same time, then technically you're already applying it to real life things. Okay, so that's about probabilities. What do I have other also? Yes, I have another one. Which ones of the following statements are true? So you have combinations here. It's basically all possible combinations. If two events are independent, then the probability of their intersection is the product of their respective probabilities. Then you have all combinations of that. It's basically 2 times 2 times 2, right? So you have independent or disjoints, you have intersection or union, and you have product or sum, right? And so I just put all 8 combinations, but in fact, only some of them are actually true. Okay. So which ones are true? So it's really about what it means for events to be independent and to be disjoint, right? Let me share how now it splits. There's two answers that seem to have a majority vote. Okay, let me not make you wait much longer. We are at the same number as earlier. So indeed, these are correct. The independence means that you have the intersection of the events that are the products of everything. You just not two, right? You could have 10 or 100 events. If they're all independent, then it means you can just compute the probability that all of them happen as the product of all probabilities, right? We say that it factors, basically everything can be factorized nicely. But of course, it's not always true because in real life, you can have actually dependencies. But if it's independent, the probability of the intersection is the product of all. And the other one is disjoint. If it's disjoint, then you can get the probability of the union with a simple sum, right? For example, the probability that it is snowing or that there's a heat wave is the sum of the two probabilities because both cannot happen at the same time. Okay? In fact, you can generalize that to the notion of a partition of the omega space. You can partition the omega space into like 10 or 100 components, right? And they are all disjoints. Together, they all cover the entire omega space. And then you can sum up these probabilities to one. In fact, what I've just told you about is a random variable. That's technically what a random variable is, right? It's technically a partition of the omega set where every partition corresponds to one possible value of the random variable. Okay. We have anything else that I could show you now? Maybe. This one. Which one of these is a 3-5 B plus tree? Do you remember the B plus trees? So I give you here 5 possibilities. And I'm asking which one is a 3-5 B plus tree? Always the right moments. So remember what this 3-5 means, right? 3-5 is the interval for the allowed number of children, right? So between 3 and 5, both inclusive. So it's either 3, 4, or 5 children per node. Then you have to remember what the plus in the B plus means in terms of the structure of the tree. And you have to remember that there is an exception for the lower bound of the interval. That there's one case in which you can break the lower bounds. And finally, what you need to think about is if the number of children is between 3 and 5, what does it mean for the number of values in every node? So they're converging. They are the other two. 21, 22, 23. Okay. Aha, it's divided. Okay. It's the second one. That is a 3, 5b plus 3. So let's look. The third one is easy. Why is the third one not a b plus 3? Maybe on Zoom, otherwise. Yes? Is it unbalanced? Maybe the way I drew it could give a bit this impression. You do have here the root, you have a level, and here a second level, right? Yes? Yes, indeed. That is another reason. So the 4 here is indeed, it's actually a typo, but this is also correct. So for this reason alone, that wouldn't be a b plus 3, right?
There is an answer on Zoom.
Yes?
So it's the 13, 4, and 15. So I think the same one.
Oh, the 4, yes, exactly. Yes, indeed. So it has to be sorted. But there is another reason that is even more visual. It is, yes? Yes, exactly. You see the values here, the blue cells, they're everywhere. That's a B tree if you have that, right? So the B plus tree means that you can only have the values here on the leaves, and you're not allowed to have the values and the pointers to the posting list anywhere else, right? But indeed, this alone is also correct, and so it's not a B plus tree. Now, so I got it right on the other ones, the 14. At least there's not this typo. Okay. Why is this one not a B plus 3? Let me try to 3, 5, B plus 3. Yes, now I know. Just needed to think a little bit. So can you tell me why the first one is not a 3, 5, B plus 3? Yes? There is. Oh, yes, okay, yeah, that would be true. But these are actually mistakes I made because I actually meant to put 22, but you're correct that this is also enough to justify that it's not a 3, 5, B plus 3. Imagine it were 22. Why would it still not be a 3, 5, B plus 3?
There is an answer on Zoom.
Yes?
So the first child on the left has more than 2 to 4 values.
Yes, exactly. If you have 3 to 5 children, then you can only have between 2 and 4 values. Who remembers that? Right? Because the values are in between the children, right? So 3 children means 2 values in the middle, 5 children means 4. So you can have 2, 3, or 4 values. But here on the nodes, we have 5 values, and that would be virtually 6 children, right? If you look at these 5 values here, it would be virtually 6 children. So that is not a lot. Yeah. And this one is not a B plus 3 because so this one would be unbalanced. See, here you would have a leaf already at a depth of 1, and here at a depth of 2, and that's not allowed in a B plus 3. This one, though, is perfect, right? Here you have 2 levels. You have always between 2 and 4 values, between 3 and 5 children, and I told you the lower bound here, it's fine with the roots to have less. So the root has 2 children, but this is fine with the roots, okay? So I wanted to rehearse that a little bit. I think the reason why I didn't fix the typos here is precisely because that just gives you yet another hint why it's not 1. So I actually never corrected them. Okay. Shall we go back to probabilistic information retrieval? Yes, we have a question. Yes? Yes, of course. So the idea is that in a B plus 3, oh no, it's not showing. I need to use my mouse. In a B plus 3, you must have all the leaves at the same depth. All the blue cells must be at the same depth. And here you can see it's right below the root at a depth of 1. And here you can see that it's a depth of 2. It's basically the grandchildren here, and here it's the direct children, and that you cannot have in a B+ tree. It must be all at the same level, right? Okay. You can ask also, preparing the slides again, but feel free to ask questions. Does anybody have questions about what we did last time? Anything that wasn't clear? Yes? The first one, right? The first one is that you have 5 values in here, and that is too much. Because look below, if you had children, you would have 1, 2, 3, 4, 5, 6. So it would be 6 children virtually. And so 3, 5 basically translates into 2, 4, 2 to 4 for the number of values, right? So here there is 1 value too much, 1 value too much. Does it make sense? Yeah? Okay, you're welcome. Okay. Any other questions? Anything that wasn't clear in the previous week? Okay. So something that I would like to remind you of is that what we've done last week was master's level, right? Because we are done with the bachelor's level material of information retrieval. So what we did last week was actually quite advanced, right? We actually squeezed a lot of formulas with Bayesian reasoning and so on. So that was actually a lot to digest, right? So now I'm going to wrap up, but before I wrap up, I just summarize a little bit to make sure that, that you are with me. So remember the idea that we have sets of documents. We started with simple Boolean retrieval at the very beginning with and, or, and not, and we output subsets of documents, but they are not ranked. Ranked came later. In order to rank the documents, we need a notion of score. And in order to score the documents, we need to accumulate evidence, right? And typically the scores were computed with some scalar product, and the scalar products are basically a very, very large sum over the terms that we compute for every document, right? So it's kind of a bidimensional thing that we do here. And we had these buckets where we accumulated, for every document we have a bucket, then we accumulate the evidence summing over the terms. Then we looked into probability theory. We saw these omega spaces with elementary events. We saw that if we define either with random variables or with simple events, we can basically write this formula, which is simply derivable with the chain rule, right? You just write it in 2 different ways, first with the umbrella, depending on the range, then the other way around. And you come up with the base formula. Incredibly useful, because the base formula gives you the ability, the magical ability, to swap the sides of a conditional probability, which is extremely useful to compute probabilities that otherwise would be almost inaccessible to us, right? Then we looked at the notion of random variables. Remember, I told you a random variable is not random, and it's also not a variable. In fact, a random variable is a function from the omega space to any space. You could also see it as a partition of the omega space. You have a partition with the blue squares, you have a partition with the red pentagons, and you have a partition with the green triangles. Because you all send them into that set S, right? And when you do that, that kind of automatically implies some probability distribution over S, right? And you just need to compute that for every value of S, which is technically every partition of omega. And in order to do that, you sum over the elementary events that have the same shape. For example, the 2 blue squares, that's 0 plus 2 plus 0 plus 2 gives you 0 plus 4 for the blue square partition. Then the red pentagon partition, that's 0.1, and the green triangle partition, that's 0.5. Who is with me? Right? So again, that's what a random variable is. And once we have random variables, we can start writing formulas like this with the probability distributions. We can also have the joint distributions with both X and Y. We can have the conditional distribution. This one is a bit more formal, but this probability of X condition of Y might at first sight be daunting, right? Because it's technically a function, so you really need a comma here, but you express the fact that you need it in a condition right here. But many people prefer to write it that way because it's a little bit more intuitive to write it that way, okay? But what you cannot do is write probability of small x or probability of small y just like that. That would be mathematically inconsistent, okay? If you see people do that, tell them, right? Okay, well, you can do it if you have a PhD and you know what you're doing, but technically when you're learning and teaching, it's much easier to actually write it explicitly. Okay, and then what we did is that we took it at scale and we imagined a giant omega space with septillions of elementary events. And that was a thought experiment because I actually have a facility in Antarctica. I think I told you about that, right? I have a facility with heptillions of little elves like this. And these little elves are basically, they each correspond to one elementary event. These are the little omegas. And when you have a random variable, it just means that the elves are associated with shapes or with documents or with queries and so on. So when we do this, for example, one of the elves or several of the elves will be associated with the query information. Some elves will be associated with the book, the document information retrieval, maybe 1,000 of them and so on. So you see, you can build the random variables in that way. And if you take one elf, this is one of the elves among the septillions. This elf has the book information retrieval, the query information retrieval, and they said its relevance, right? R is 1. This is one of septillions. Who is with me? That's how I think of the omega space. Makes it much easier to reason in my mind. What's very important is that if you look at one elf, it's deterministic. If you look at one elf, there are no probabilities. The probabilities come from the many elves, the fact that you have septillions of them, and they each have some probability. We can assume it's uniform, but it doesn't have to be. Okay. And once we have all of these septillions of elves in my facility in Antarctica, we can start writing this here that are basically mathematically consistent, just based on this probability distribution over the elves and the definition of the random variables that associate the elves with documents and queries. And so when I want to compute the score of every document, what I do is that I take my documents. So here I have D, F, D, G, and E. These are my 4 documents that I'm considering. And I'm computing for every one of these documents the probability that given query Q, little q is what the user entered on their computer, given the query Q and given the book for which I'm computing the score, what's the probability that it's relevant? And that I can compute with the elves, right? It's just mathematical. I just use my facility in Antarctica, and then I sort by whatever number these things output, and I return the documents that have the highest probability of relevance. So F would come first, then D, then G, and then E, right? Okay. So technically, I could build a Google like this. It would cost a lot of money, but I could do it. However, what we realized is that by thinking a little bit, we can actually simplify these formulas to the point that I can actually pretend to have this facility in Antarctica that actually doesn't exist because I can simulate it with a trick, a mathematical trick in reality. So the idea is that I consider these documents to be vectors with Booleans instead. So I even narrow down my when I have one elf, it can even tell you this term is in the document or it's not. And the same for me. So what we did is that on the left here, you have what I want to sort by. That's the probability that the document that I want to compute the score of. I'm going to do it for every document, right? But this is currently document small d. I want to compute the probability that it's relevant. That's my score. And we spent last week an entire hour squeezing that formula and trying to turn it into something simple that wouldn't need the little elves, right? And so the first thing we do, as is always the case in that kind of tricky problems, we swap the sites. This is the magic of the base formula, right? I can always have this extra condition on Q, but I basically swapped the size in here. Then what I did is that instead of looking at the probability, I looked at the odds. because if I look at the odds of relevance, I get rid of the denominator. That's the first trick. So the denominator goes away like this, if I look at the odds. And sorting by the odds is the same as sorting by the probabilities in terms of the order of the results at the end. By the way, last time I didn't realize I could have told you sooner, but this doesn't depend on D. So actually I could even have thrown that away from the very beginning. I don't know why I didn't, but anyway, this can actually already go away. But we are left with this. So what we did then is that we took the probability that we have a specific document, and then we used that. I'm done talking. Why am I done talking? They will lower my hand in 1 second. Okay. Maybe it thought that I was raising my hand. Okay. But I hope I'm not done talking. I mean, people can hear me on Zoom, right? Okay. So we take the probability that we have a document. Awesome, you can hear me. So we take the probability of a document and we turn it into a huge product. That's the question on independence, right? If I take a pair of scissors and I cut my book into little tokens, I will have maybe 1 million tokens. I can actually compute or re-express the probability that the document is that book by just independently computing the probabilities that it contains each terms, right? It's a huge assumption. Of course, it's not true in reality, but we assume that the terms occur independently in documents. If we assume that, then the probability of the intersection that it contains or doesn't contain each term as desired turns into a product. And that's what I give you as a visual last time with an example of document there. And we can turn the probability that it's that document, Polyban is unexpectedly working today, as a probability, a product of probabilities like that. Then when we do this, we get this out. Now it's a product. What we did next is that we cut it in two. We just put on the one hand all the terms that are in my document, and on the other hand all the terms that are not in the document. It's just a partition of according to do they appear, do they not appear in the documents. Then we gave a few names like Pikachu for the red part, and then Yukachu. Don't know if that means anything for the other one, right? And that's called the contingency table. Basically, it's really the probability that the case term is present given relevance or given non-relevance, right? And if we would know these values, then we would be able to compute that product, right? Then there's a few simplifying assumptions that are made in the book. There is one that they do without telling you, and I don't know why, they just drop the Q. But they don't tell you they drop the Q, but actually they do it. But this is an assumption, right? That this contingency table does not depend on the query. It's always the same one. You can argue that that makes sense. You can argue that it doesn't make sense, but this is what we do here. So we drop them, and then we end up with this product here, right? All right. With a few simplifying assumptions. Then we have here the terms in D on the left. And then I did something scary. If you can remember, I basically took some ugly formula, and whatever that ugly formula is, I divided by it and I multiplied by it. So dividing and multiplying by the same number doesn't change anything, right? So I can always do that, whatever ugly formula I put in there. So I just put that ugly formula, I divide by it on the left and I multiply by it on the right. Of course, that ugly formula isn't any ugly formula. It's chosen in such a way that it actually simplifies a few things over there. And how do we see that it simplifies a few things? Well, if you see what's going on here, it's just right there. You can see that there is no D here. Do you see any D? There is absolutely no D. So it means that all that part on the right, we can get rid of. That goes away. So that's awesome, right? Because now we can focus on that. So we are basically making good progress on managing to do without the else. Now, do you remember that when we computed scores in the past, this evidence accumulation and these scalar products, we summed over things? Do you remember that? When we accumulated in the buckets, we kept summing. It's a very big sum. But now I have a product. Now, do you know the magic to turn a product into an addition? Well, that's known as the logarithm, right? So we just apply a logarithm and we get a sum, right? Now it starts resembling a little bit what we know how to do. I just have this sum, right? If I take the log, I have a sum. For all the terms that appear in the query and in the document, I sum over this ugly thing on the right, log of pk divided by minus pk minus blah, 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 blah. It only depends on k, on the term, and I just sum over that for the terms that are in the document and in the query. Who is with me? That is much simpler than the septillions of L's, right? Now, you can interpret that actually as pk divided by 1 minus pk, that's the odds of containing term k in relevant documents. Remember that an odd means that you divide the probability by 1 minus, that's called an odd. And then we have the odds of containing term k in non-relevant documents, right? So it seems like we're always almost there. The only problem we have left is we don't know the value of pk and uk, right? So we need to have numbers to put in there in order to do it, right? That's basically this contingency table. Let's call it ck for now. Let's call that ugly thing ck. And now I have a sum of weights called ck on the terms that are, the terms k that are in the query and in the document. Right? You see what's below the sum. I have here a condition that k must be in the document for which I'm computing the score, and it must be in the query. Now, if you interpret that, that sounds like something we've already seen, right? Because now if this ck that depends on the term, if in my standard inverted index, I would put it together with here with the document frequency, all I need to do is sum over the terms for each document. So I have my document buckets, and for every document, I sum the ck's over the terms that are in the query. That is what I'm doing here. Who sees that? Right? It's the same thing. I'm just looking at the terms in my query. I look at the posting list, and for every document in the posting list, if that document appears in the posting list for term k, then I accumulate the evidence, ck, into the bucket of the document, right? That actually looks great because we know how to do this. We know how to implement this. We've already done that for the vector space model. We already have the standard index and so on. The only thing is we don't know ck. If we would have a value for ck, that would be fantastic, right? You can also then express it as a scalar product, because once you have seen that, that's technically a scalar product. You can actually view it in that way too, because the scalar product is just the sum of the products of the coordinates. And here you just have ck multiplied by 1, technically. Okay, so we are left with one problem. How do we know what to put for ck? How do we compute all the weights that we need in there? Now you could tell me, okay, machine learning. Yes, you would be right. You can do it with machine learning. But let's try without machine learning first. So we have this contingency table with the probabilities that the terms are present or not conditioned on relevance. We could take, in these cases, when you want to estimate probabilities, a statistical approach, right? For example, imagine that I give you a coin, and the coin might not be, it might be biased, right? It might be that it's not exactly 1/2 because there is some density difference inside the coin. How do you evaluate the probabilities that it's heads or tails with the coin if I give it to you? How would you do that? Evaluate the probabilities, the two numbers. You just toss it thousands of times, right? Just keep tossing it, tossing it, tossing it, tossing it. You record heads, tails, heads, tails, heads, tails. Then you count the number of heads, you count the number of tails, and you do the division. And that gives you an estimate of the probability, right? That's called the maximum likelihood estimation. So it means that the trick to estimate a probability is to just use statistics. You just repeat and repeat and repeat and repeat very large number of times, and then you count. So the first idea that people might have is to just use statistical estimates. Instead of looking at the probabilities, they look at statistics. For example, if you sum over everything, a term is present, not present, and so on, technically, you end up with the total number of documents, right? Then if you look at present absent, that's basically the document frequency. It's the number of documents that contain or do not contain the term, right? So if you look at the blue part in here below, you can split n, the number of documents, into those that contain the term, but that's the document frequency. Remember, the number of documents that contain a term is the document frequency. With me? Right? And here it's n minus, it's just the difference. But the problem is that then you start hitting an issue, because here you just make up some number s that you don't know what it is. Then you have n minus s, and then you can complete this and another small s in here. But then you're back to square one because you don't know what to put for small s and big S. Now, you could, of course, again, either use machine learning or test techniques for that. But let's try to simplify to not have to actually find a value for small s and big S, right? So in the end, this is what you want, but you don't know small s and big S. The document frequency, that you can find out. Just look at the collection and count. So that's easy. N is also easy to find. But what do we do about big S and small s? That we don't know. As a reminder, the goal of that is to then compute this. That's the CK that I had based on PK and 1 minus PK. Now, if I replace PK and UK with this, I end up with this formula right here, right? That would, if I had uppercase and lowercase s, then I could do this. Now, a trick, assuming we have that for now, there is one additional step that is done that's called smoothing. We would actually add a plus 1/2 everywhere. Let me explain why we do this. We do this because when you want to estimate statistics like that, like tossing the coin, you basically have the actual values that you don't know. This is what's hidden, right? This is what you're looking for. You're trying to find a way to access these values, but you don't know them, right? These are my little F's in Antarctica. And if in order to compute them, you want to just estimate statistically by repeating, then the problem is that the number of times you can repeat in practice will be bounded, right? You cannot do it forever. So what's going to happen is that you will slightly be biased, right? It means that there might be terms that are so rare, right? Like supercalifragilistic espialidocious, that's a super rare term. Maybe there's only one document that contains it. And the problem is that it's very likely that in your sample that you have, you're not going to see it at all. So it means that your sample is always a little bit biased because you have a bit more of the terms that occur often, but you might see 0 of the very rare terms. It's just because your sample is too small. In that case, there is a trick, is to basically add some uniform probability and a mix of that. It's a mix of uniform probability and the statistics that you observed. So you basically just add 1/2 everywhere. And it turns out that when you do that, it's a simple trick, but it brings you closer. You see the purple adjusted adding 1/2 everywhere is now closer to the exact values. That's called smoothing. Who is with me? Right? So you just imagine that you have on the one hand your statistics that are biased. On the other hand, a uniform distribution. You just go for the middle of that, in between the statistics that you obtain from your sample and the uniform distribution, and you just are in the middle. You mix the two. Okay? Then you can, of course, take different weights for the two and move around, but this is the idea of smoothing. Okay. Now, having said that, in practice, there are people who suggested to simplify a bit more. I might say it's very courageous to push it that far, but you will see it's actually incredible. Some people suggested to get rid of the uppercase S and lowercase s by just suggesting that if a document is relevant, then maybe the query terms appear in there, maybe a term appears in there, or a term doesn't appear in there. Maybe, maybe not. 1/2, 1/2, right? It's a huge rough approximation to do that, right? But they just did that, right? So 1/2, 1/2. It's a toss of an unbiased coin. So this is the first simplification that they did, but we still have an S and a small s in here that are left. But then what you can do is just get rid of it, saying, okay, let's assume it's negligible, this big S and small s, and you're just left with document frequency and n minus document frequency. Now that's great because we got rid of the uppercase S and lowercase s. Again, I suspect that the way it's done is actually the other way around. Like, how could we get rid of lowercase s and uppercase s? Let's assume we can get rid of them, and then you try to justify, right? But you will see that actually it will make sense if we do that. So now this is our new contingency table. Now we can compute, who agrees we can compute CK with that, right? Because my CK here was just this, right? But now I can replace all of these numbers here with what I have simplified, right? So let me go back to here. There is one more simplification that actually can be done, is that in practice, for most terms, if you forget about the stop words, do you agree that the document frequency is negligible compared to the whole collection? Who agrees with that? If it's not a stop word, right? You might have 1 billion documents, but then you take a word, maybe there will be 1,000 documents that have it. So it's negligible before 1 million. Who agrees? So I can get rid of the df here. You agree? I can just say, okay, it's roughly n. So now, if I plug that back into my formula, that's I had the pk over -1 minus pk and uk over 1 minus uk. But now I replace the pk and the uk with these things in there. So on the left, I have 1/2 divided by 1/2, right? The odds of a uniform probability 1/2, 1/2. It's 1/2 divided by 1/2, that's 1, right? So we have the log of 1. And then we have dfk divided by n, right? So pk divided by 1 minus uk divided by 1 minus uk. That's the log of dfk divided by n. Log of 1 is, what is log of 1? I hear so, all at the same time. Log of 1 is 0, yes. So I can get rid of it. And if I swap the sign, I get this. It's called the retrieval status value. So I'm summing over the terms in the query and the document. Does anybody recognize this log of n over dfk? What is that? We've seen that before, right? What is it called? On Zoom, maybe? Come on, you know that. What is log of n divided by the document frequency? Yes? It's the IDF, yes? That's the IDF. So now we are summing over the IDFs. So do you see where we arrived at? We basically sum over the IDFs. This is, in fact, the vector space model with the smart skin BTN, BTN. B means that we take 1 for the term frequency, Boolean. T means that we take the inverted document frequency, and then we take the same for the query. Okay? This is amazing. We basically justified why IDF makes sense with my little elves in Antarctica, right? So now when people ask you, why do we use IDFs in the terms? It's because of the little elves in Antarctica, right? That's the reason. Okay, you deserve the break. Then I just show you a little bit of how we can optimize slightly, and I'll finish. Okay, so I'll see you in 15 minutes for the remainder of the lecture and language models.